let's do a problem having to do with radical polymerization. Recall that in a polymerization reaction, there is a monomer, and then the monomer is joined to another monomer in some regular way, and what you end up with is something that's composed of many monomers linked, and that's called a polymer. So in this particular case, the monomer will be this molecule. Do you know what this molecule is called? This is styrene. It's an alkene substituted with a benzene ring with a phenyl group. And what we're going to do with the styrene is we are going to treat it with a little bit of a radical initiator. In this case, we'll just use a peroxide here, which I'll just indicate generically as ROOR. And then we will heat this up a bit. There's just a little bit of this. So you need that to get the process started, but then it's just used one time. Okay? So maybe by analogy to what we looked at in class today, go ahead and see if you can come up with the polymer that is generated. And maybe you can guess what a good name for this polymer would be. Can you guess what the polymer is over here on this side? Poly something. It's polystyrene. And if you take this polymer and you can manipulate it and you can make it into a foam, and you can mold that foam and make it into little cups and stuff. So you've probably used at some point in your life a polystyrene coffee cup. I know Starbucks doesn't use polystyrene, and maybe polystyrene food containers have even been banned in New York City, I'm not sure. But if you know those kind of clamshell hamburger containers, those are also made out of polystyrene. Anyway, can you come up with some reasonable way to get to a polymer of styrene? The initiating event is going to be homolytic cleavage of the oxygen-oxygen bond in the initiator. So remember, one electron goes one way, the other electron goes the other way. So that's the initiation step. You get one of those and a second one there when this thing cleaves. And so here is your initiating radical. What do you think this radical would do in terms of reacting with styrene? And a couple things to keep in mind. First of all, the benzene ring of styrene, remember we have a sense that there's a special stability associated with this benzene ring. So the benzene ring remains unaffected in this process, although it does have an influence on the reaction. And then my other recommendation is fill in the hydrogens on the double bond and think about where the initiating radical would add to the double bond to give the better of the two possible resulting carbon radicals. Well, let's fill in the hydrogens. There's a hydrogen here, and a hydrogen here, and a hydrogen there. And so now what we want to do is we want to add this radical to this double bond. Let me number the carbons maybe to help keep track. There's carbon 1, there's carbon 2. We want to add the radical in such a way to get the better possible radical. So what do you think? Should we add RO dot to carbon 1 and leave a dot on carbon 2, or vice versa? Add the oxygen dot to carbon 2 and leave a dot on carbon 1. So maybe with that you can push the arrows for the proper choice there. Let me redraw my styrene molecule over here, maybe just to make things a little bit less crowded. There is styrene, and maybe this drawing is indicative of which regioisomeric pathway we're going to take. Here's carbon 1 and here's carbon 2 as I numbered before. And as this picture maybe is oriented to show, the radical is going to add to carbon 1 because I want to end up with the better radical, namely on carbon 2. All right? So the initiating radical, this oxygen makes a new bond to carbon 1 using this electron plus 1 electron from the pi bond. The second pi electron goes to carbon 2. So if you haven't already, please draw the result of that. Here's my initiator. Here's carbon 1. There's carbon 2. Here is the benzene ring of styrene. Let me fill in all the hydrogens here. There are 2 hydrogens at carbon 1. There's 1 hydrogen at carbon 2. And here is my dot. So the next thing I want to ask you is take a look at this radical intermediate and tell me, as far as carbon radicals are concerned, how would you assess the goodness or the energetic favorability or stability of this particular radical? What kind of radical is it? This radical is secondary, to be sure, so it's a secondary radical. But is that all that it has going for it? No, it's also benzylic with respect to the phenyl ring. What does that mean? Well, that means that it's resonance stabilized. So the next job for you here is, can you draw appropriate resonance structures of this benzylic radical to convince your viewer that this really is a resonance stabilized entity? We're going to write resonance structures in the usual way, except we're going to be using these kind of fishhook things. So I can delocalize my dot there, and then I can come here and do that, and then do that. So this just says use one of the 2 electrons from this double bond to make half of a double bond this way. The other half comes from this dot, and then the second electron from this bond goes on to that carbon. So let's keep going here. So there's going to be a dot there. And now maybe I've convinced you. Where else can this dot go? Well, this dot could end up on this carbon, and this dot could end up on this carbon as well. So be sure that you can draw, I won't do it here, but make sure you can draw 2 more resonance structures of this benzylic radical. All right? So a benzylic radical really is a pretty good radical as far as radicals are concerned. Well, now I have this benzylic radical. It does have these other resonance contributors, but most of the dot is localized on carbon 2 because that allows you to preserve the benzene core. And so remember, we're trying to make a polymer. Let's not forget about that. So so far I've consumed 1 molecule of styrene. Presumably, I have a lot more styrene around. So I'll just write styrene in this way. So here is another unit of styrene. Here is your radical. So how would this radical react with styrene? And let's keep our numbers on here. There's carbon 1 of the next styrene molecule. There's carbon 2. What do you think would happen next? This radical should add to styrene, and it should add with the same regioselectivity that we saw before. Namely, the new carbon-carbon bond should be formed between here and here, and that allows you to make a new benzylic radical with 2 units of styrene incorporated. So see if you can draw that product. when you're doing polymerization reactions, it's very helpful to keep the numbers here. So there was carbon 1, there was carbon 2. There's a phenyl group at carbon 2. Then came another carbon 1 from the second molecule of styrene, and another carbon 2 there. There's a hydrogen there. There's a second phenyl group there, and there's a dot there. Okay? And then guess what? You can keep going, right? So you could add to another molecule of styrene, etc. So can you come up with a structure down here that represents the polymer? Maybe let's have it have, I don't know, what happens after you repeat 3 more times so that you would have a total of 5 units of styrene in your growing polymer chain? Can you draw that? Well, down here you would have you would have 1, 2, and then 1, 2, that's the second unit. Then 1, 2, that's the third. I'm going to have to squeeze it in here. 1, 2, that's the fourth. 1, 2, that's the fifth. And then notice, because of the regioselectivity of this process, namely the dot will always add to carbon 1 so as to put the new dot on carbon 2. It's regular, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And the phenyl group is, of course, on 2. So then I can decorate this chain here like this. And then there's my dot over here at the growing end of the chain. And so this could continue a bunch of times. Notice on the very end of your chain, there's an OR group. But because the chain is so long and it only has one end, well, it has an end on the other side as well, right? So at some point, the chain's going to have to terminate in some way. But really, the properties of the polymer are dictated not by what's way on the ends, but the bulk of the polymer, which is really this regular type of structure. Okay? All right. One final question about polystyrene. Are there any stereochemical features associated with polystyrene? If you look at this, don't forget that there's a hydrogen at each of the carbons 2. There are also 2 hydrogens at each of the carbons 1, but let's focus on this. And notice each of these carbons is a possible source of stereochemistry. So you could imagine, for instance, a polymer as shown with all the phenyl groups. Somehow they've been oriented all toward us. You could imagine them alternating forward and back, or some other pattern, or else maybe it's just completely random. So depending on how one polymerizes different monomers, it is sometimes possible to control the stereochemistry. All right? In just polystyrene, regular old polystyrene, the stereochemistry is not controlled, but in some other polymers, it is. Let's use a reaction that we're going to learn much more about next semester, but that is also very useful for making polymers. Imagine that we have this type of molecule. First of all, what class of molecule is this? This functional group that you see here, what kind of compound is this? This is a carboxylic acid. Notice it does have an OH group, but it's not an alcohol because the OH group is attached not just to a regular carbon, an sp3 hybridized carbon, say, but to a carbonyl carbon. So this special case of having an OH group attached to a carbonyl group and then an R group on this side, this is called the carboxylic acid. And then let's combine that with this molecule. So this also has an OH group in it. But now you just have an R group attached to the OH. It's not a carbonyl. So what kind of molecule is this? Well, this is an alcohol. So here's a reaction that we'll learn much more about and more detailed information about next semester. But let's see if you can write down the product. So let's say you combine a carboxylic acid with an alcohol. And I've put a little X in this oxygen because this oxygen is part of the product that you're going to write, part of the organic product that you're going to write. So make sure that whatever product you write, the organic product has this oxygen with the little X in it. And the byproduct in this case is a molecule of water. So sometimes this type of reaction where you take two components and you attach them together and you get rid of or extrude a molecule of water, it's often called a condensation reaction. So you can think of this, just really condensation of water as the reaction proceeds. You might condense water on the sides of your flask or something like that, or you might boil it off and condense it in another flask. So this type of process can be referred to as a condensation reaction. So what do you think the product of this would be? You don't have to think about it mechanistically, really, just in terms of what are the pieces, what do you think the product should be? And I'll give you an additional hint, other than it has the oxygen with the little X in it. It's also a class of molecule that you've probably, I'm sure you've seen before. Well, if we're going to keep this oxygen, maybe we have to get rid of this hydrogen. And then where's the rest of water going to come from? It might come from here. All right? So again, this harkens back to the bad old days of organic chemistry, where organic chemistry got its terrible reputation, where people would just have two molecules. You would put a little box around the pieces that were getting lost, and then they would magically just vanish, and the product would appear. And then the student was just supposed to memorize this, and then another reaction like that, and another, and another, and another. And it just became this enormous and tedious memorization game. So we try to organize things more mechanistically, but in terms of just thinking about the product, let's kind of go back to the ancient ways. So if you were to remove the OH and the H, maybe that's another hint. What product would you expect to form? Well, the product would be one like this. So here is the part that came from the carboxylic acid, and then over here is the part that came from the alcohol. And do you know what this type of functional group is called? So you've got a carbonyl with an R group on one side, and on the other side, not an OH like you had in a carboxylic acid, but an R prime type of group. This product is an ester, okay? It's not an ether. In an ether, you do have R prime OR, but this is not just a normal R group. It's a carbonyl, so that has a special name. This is an ester. So this is an esterification reaction of a carboxylic acid plus an alcohol, removal of water, and formation of an ester. All right? Okay, so why do we need that? Well, let's come over here to this other board. Let's imagine that we had a molecule like this one that has not just one carboxylic acid in it, but two. And let's say we combined that with an alcohol, except let's make the alcohol have not just one OH group, but a second OH group as well. So, you know, I could number this carbon 1 and this carbon 2. What do you think would happen if I took these and I combined them? I removed water. The claim is that I will get a polymer. This type of polymer, because it's formed via a condensation reaction, can be referred to as a condensation polymer. So can you propose a structure for what this polymer would look like, just using by analogy this esterification reaction? Remember, an alcohol will react with a carboxylic acid under the appropriate conditions to make an ester. So can you draw this condensation polymer and maybe give it a name, a poly something? This dicarboxylic acid could condense with the OH group of the alcohol to make an ester between this oxygen and this carbonyl. And then you would have another OH on this side, which could do the same. And then this dicarboxylic acid has the ability to form an ester on this side and an ester on the other side as well. Okay? So maybe, let's see here, if we start with this. So here would be the oxygen of the alcohol. That oxygen is connected to carbon 1, which is then connected to carbon 2. On carbon 2, there's another O. And then this O would be attached to the carbonyl of another molecule of this originally dicarboxylic acid. And then, and so on. Here's carbon 1, here's carbon 2, there's another O, etc. over there. And then over on this side, the polymer can continue like this. There's two carbons here, carbon 2, carbon 1, O, etc. Okay? So in drawing a polymer, sometimes it helps to abbreviate the drawing by finding the shortest repeating unit and putting brackets around it. Okay? So see if you can do that. See if you can find one subunit of this polymer where if you just repeated that subunit n times, you would generate the complete structure of the polymer. Well, we might be able to start right here, right? So let's start our bracket there. Or maybe, hold on, let's see here. Let's start right there, since this carbon, right, came from here, but this oxygen came from the alcohol. So here's one unit of what was originally from the dicarboxylic acid. And then here's one unit there, 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 and there. There's one unit of the original diol. And so then I could close the bracket right there. And you see when I repeat the next one, I start with this carbonyl. There it is. So I could just put, I'll put it in a different color here so it doesn't get lost. I could just put a little subscript n to indicate that this polymer is formed by repeating subunits of this type. Notice, what type of functional group is this right here? It's an ester. Here's another ester, here's another ester. So what would you call this? A poly what? Well, this is an example of a polyester. Okay? This particular polyester is called Dacron. So you might have heard of Dacron as a type of substance that is used to make fibers, and then you can spin those fibers into cloth and so on. So your polyester suit, maybe it's made out of this stuff.